Hello and welcome to the recording of the webinar from July 8th on how to monitor the effectiveness of your IQCP. Much of this material is newly recorded, the part specifically with the QC simulator for clarification. We join the original recording in process after the completion of the mandatory conflict of interest disclosure slides for the purpose of PACE credit.
Our objectives today are exactly the same as they were 2 weeks ago. The process we're going to follow is completely different. This time, we don't talk about theory, we're going to delve into practice. We're going to start with 3 fundamental facts about numbers that you should know, review quickly the fundamentals of risk management, talk about setting medical goals and acceptable risk, and then go into 3 separate components of the QC simulator. One that will let you evaluate current risk, one that will then let you optimize QC rules, and the final tab we'll use to evaluate potential risk. We'll learn this formula: patients at risk equals runs to reject times patients per run. If you want to evaluate risk, it's a mathematical formula. From that, you can calculate the cost to control quality. Well, actually not from that. From that, you calculate the potential cost of failure to control quality. If you're not going to detect your error for 10 runs, you have a huge potential cost. You can compare that potential cost of failure to the cost to control quality, what you're spending on quality control, and you'll see how to optimize the QC frequency. That really is the last piece of the puzzle. 3 fundamental truths about numbers. Every number is one single piece of information. Every number conveys one single something. Every number can be associated with a specific what, where, when, who, and how. So one specific piece of information from one number. Every number needs a reason that you care. Try answering these questions for all the QC numbers that you look at, and then have some fun and walk through the lab and ask your friends and colleagues if they agree. What does this number actually tell you? Why are you looking at it? Why does it matter? Why do you care? Each number is a thing of awe. That simple phrase pretty much single-handedly revolutionized being able to teach the students. I've mentioned to you I've taught for over 10 years at an online master's level course. And with this simple phrase, we could categorize the numbers and people could understand how QC works. Each number comes from either opinion or fact. Each number conveys either where you are, where you want to be, or where you expect to be. If you can categorize the numbers into those 3 categories, you can manage quality. You see, numbers are absolutely meaningless without you. You look at that number 75 and it means nothing. But humans have a built-in capability to just apply this logic. Is this what you expect? Is this what you want? Let me give you some examples. The balance in your bank account. See how quickly you applied those standards? The balance in your teenager's bank account. The math grade on your teenager's latest report card. Some of you are ecstatic, some of you not so much. The math grade on your sister's teenager's latest report card. You see how this works? The speed you're driving on the highway. That 75 now suddenly has a totally different meaning if you're south or north of the Canadian border. The speed you're driving in a school zone. The recent mean of your glucose QC sample. Again, that has a different meaning if you're north or south of the border, but once you know what you expect and what you want, it's very easy to look at where you are and see if that's where you want to be and if that's where you expect to be. Medical goals define where you want to be. So the medical director, this is a medical decision, in collaboration with the medical staff would say, for these analytes in these settings, I want to use these goals and I will accept this level of current risk. Remember, there are two components to risk management. You've got the current risk that comes from the analytical process. If you were doing no QC at all, how many bad results would the instrument be turning out? And we do all of this, all of the key staff training, method validation, daily QC, proficiency testing, inspection, accreditation to make sure that QC, that analytical process is working. We've never QC'd the QC process. Nobody's ever said, hey, will that QC really detect a clinically significant error? And that's exactly what we're going to do today, and that's exactly what risk management brings to the table. Both in IQCP and EP23 is at the least the ability of QC procedures to detect medically allowable error should be evaluated. From the patient's perspective, is my risk of receiving a medically unreliable result today acceptable? And will it be acceptable if the method fails tomorrow? Ray, can you please launch this poll? Using Sigma, Six Sigma, a Sigma metric as you know it, answer this question to the best of your ability.
28%, 31%, 19%, 14%, and 8%.
Very, very interesting. What I want you to take from this now is just that different people have different standards. Can you go please, Ray, straight to the next poll?
Sure.
When you voted, were you referring to a short-term sigma, a long-term sigma, or do you not know the difference? Aha. And by and large, the most popular answer is, what's the difference? You're going to see later on what that difference is. And the one I should have put in here is, do you use sigma? But everybody, I think, now is familiar enough with the concept that this is going to prove very interesting. So we're going to talk about those in context with the simulator.
This is actually a re-recording of Prof Zoe's QC simulator. I want to make this a little slower and clearer than what we did in the original webinar. We're going to go through the objectives of the webinar, this time with real numbers and with visuals. Tab 1 on current risk answers the questions, how good is good enough? And is the method good enough now? The second section deals with, would you know if it wasn't good enough? How to design the QC, and you're going to design QC processes from a simple table based on margin for error. Finally, we come to potential risk, where you bring it all together. You can compare the cost to control quality with the potential cost of failure to control quality. And the final tab is simply some calculators I've thrown in so you can check the math on a few things you may be doing. Once we go into the simulators, they follow this same principle. A number is a thing of awe. Numbers come from opinion or fact. So if a number is selected from one of several possible choices, that's based on opinion. The lab director defines the source of the medical goal, the true value, and the acceptable risk limit based on medical opinion. You cannot calculate medical opinion. You cannot calculate acceptable risk or medical goals within your lab. That would be like trying to calculate the speed limit based on the speed you've been driving. There are only 4 numbers that the lab controls. Your opinion drives these numbers, nothing else. So let's go into the simulator. Tab 1 deals with current risk. I've divided it into sections just so we can take this trip rather slowly. We start with dealing with the risk drivers. These numbers drive current risk. We're going to give you, as we go through, more numerical information and more visual presentations to see exactly what's going on. And based on the numbers you put in, without seeing any of this, the computer can decide if risk is acceptable, yes or no. It makes that decision based on these risk drivers. The peer mean is the best source of the true value. I used to teach, here's 5 ways to select the true value. The peer mean is the best source of the true value. We used for the 10 years we practiced this in the Cochrane Region program, we would set the peer mean on month 1 or month 2 of a new lot number, and it would normally stay consistent throughout the lifetime of a 2-year control. Current mean, however, changes with every reagent lot change, as instruments change, as people change, the current mean changes with every calibration a little bit. The current SD changes. These are based on facts that come from the instrument. The medical goal and the acceptable risk level are based on the opinion of the medical director. Every time you change one of those 5 drivers, the assessment of whether risk is acceptable or not can change. We're going to start with a current mean value of 100. And at that point, the risk is acceptable. The medical goal is plus or minus 10. So obviously, if my current mean is 90, that's not acceptable. If the current mean is 105, however, that mean is acceptable. But if the current mean is 105 and the SD is 3, then it's not acceptable. That is all based on simple logical mathematics. Now let's take a look at the actual numbers and how the computer makes the determination if risk is acceptable, yes or no. It's a simple calculation. Remember, risk estimation is the process used to assign values to the probability of occurrence of harm and the severity of that harm. You can mathematically calculate the probability of occurrence of a medically unreliable result, a result that fails the medical goals. Risk bars and risk charts simply show you that calculation, show you what's going on. They show you where you are versus where you want to be. These are the risk bars, these are the charts. Every time you change the mean or the SD, the visual information that you receive here will be different. Okay, let's take this live. This is Prof Zoe's QC simulator. We're on the tab for current risk. We have the same risk drivers you've seen in the PowerPoint presentation. These are the risk bars, the risk evaluation chart, and the calculations. We're starting where we were there with a current mean of 96 and a current SD of 1. Watch the visuals and the numbers. When I change the current mean to 100, now you can see that on both the risk bars and the risk chart, it's centered around the true value, which is the peer mean. If the peer mean was 98 instead, then this would be a positive bias. If the peer mean was actually 95, this would be a stronger positive bias. But if the peer mean was 106, then we have a negative bias. It's the relationship between the peer mean and the current mean that determines accuracy and bias. I'm putting this back to 100. I'm going to move the current mean up now to 104. This, folks, so now the current mean is 104. You can see it has a positive bias. Just looking at the risk bars and the charts, you can see it's quite a good distance from the red lines that are the failure lines. When you come to the numbers, the current risk is 0%. The margin for error is 4 SDs. That means it can shift 4 standard deviations before risk becomes unacceptable, and a sigma value calculated from the same numbers would be 6.0. So this is a 6 sigma method. So let's see what that means. It says the margin for error is 4. It can shift 4 SDs. Let's try it out. 105. And that looks fine. The risk is still 0%. The margin for error dropped to 3. The sigma dropped to 5. If I go up to 106 with a new calibration, The risk is still acceptable. You can see visually that it's getting closer, and now it's not quite 0%. This is still a margin for error of 2 or a 4 sigma method. So we've shifted 2 SDs. Let's go up one more to 107. This method can only shift 1 standard deviation before it will fail. This is a 3 sigma method. The risk is still acceptable even though it's much higher than it was before because it's still within the acceptable risk limit. And if I go up that 4th standard deviation to 108, now the measured risk, 2.275, is equivalent to the acceptable risk that is not acceptable, and you should stop. The math is just that simple. Let's bring this, oh, wait a minute. Okay, I'm going to bring that back to my 104 or 105 again. And you see we have a risk value of 0. My sigma is 5, my margin for error is 3. Bring it up to 106. This is a 4 sigma method on one side of the street. But what if the clinical chemist crosses the street? What if the clinical chemist believes that we should be using biological variation and comes here and says that the desired biological variation allowable limit is 6.96? So I'm going to come back over here and enter 6.96 as my medical goal. The same method that is acceptable on the north side of the street is unacceptable on the south side of the street because when you set your medical goal based on the biological variation limits, this is now a method with a sigma of only 1. The margin for error is -1, and 16% of your results are already failing, if you believe in biological variation. However, if you bring in a new clinical chemist and they believe in CLIA instead, then you're perfectly fine. The question you want to answer is the risk of a patient receiving a medically unreliable result acceptable? Yes or no? The risk of a patient receiving medically unreliable results depends on the physicians who are going to make the decisions about those patients, much more so than on the personal opinion of somebody who's arbitrarily setting medical goals so that one side of the street things fail and the other side of the street things pass. There really must be a medical goal based on medical opinion. We're going to go back to the easy way. We'll set it back to the CLIA limits. But now I'm going to come down here and I'm going to say, I'm going back up to 10. Well, no, let's bring the SD up this time. That looks like more fun. I'm going to increase my standard deviation to 1.5. Now, if I believe that the acceptable risk level should only be 0.1%, this method is unacceptable. Is this a reasonable or unreasonable assumption? Is it a decision that should be made within the medical lab, or is it a decision that should be made by the medical director? Should it be weighed with the consequences, the cost of the results that are being reported? How many results will be reported if you set your acceptable risk level here versus at 2.23? Those are the questions. Now we need to go into more numbers to answer those questions. So now you can see the final chart, the final visual, and this is the QC chart, or the change chart as I like to call it. The QC chart has the measured mean at the center, the current mean, and uses the current SD limits to set the plus and minus 2 SD that are shown here at the red lines. This is what you expect. After this blue line, I've simulated a shift to unacceptable risk. After the blue line, one of the 20 results afterwards exceeds the allowable error limit. That means 5% of the results are clinically unacceptable. What we're seeing on this QC chart is exactly what people think they always see, that shift in the mean would be noticed immediately. But watch what happens as the gap between where you are now and where you would be if the method failed becomes smaller. Let me shift that up to 104. Now, the sigma is 6, the margin for error is 4. We have a wider spread to the data. Let me shift it now up to 105. Now you're seeing that of the 20 points afterwards on the QC chart, there's one that's not flagged, but still 19 are. You'd probably see that in the first run. What if I have a mean of 106? Well, that's a different situation. Now, only 50% of the results afterward are flagged. That's because the margin for error is 2 SD. If it shifted 2 standard deviations, the method would fail. An unacceptable risk level would exist. If it shifts 2 standard deviations, you know this from the statistics. If the new mean is 2 SDs higher, 50% of the results are above the mean, 50% are below. There's only a 50% chance you're going to detect that error. So although the risk is acceptable now, this QC process is not effective to detect this shift in the mean. And if my current mean drifts up again to 107, you can see that this method can only shift 1 standard deviation before risk is unacceptable. There are only 4 out of 20 points flagged after that shift. The odds of detecting this shift in the first run are about 25%. This is a 3 sigma method. Now let's go back with this in mind when you can see the relationship between where you are now and the probability that you're going to detect unacceptable risk if that risk occurs, depending on the current mean, the current SD, and that determines the margin for error. The margin for error determines the probability that you're going to detect simulated clinical shift in the first run. These numbers really do matter. The question becomes, what is the acceptable risk? Risk management is black and white. It's a simple matter of comparing the estimated risk to the given risk criteria to determine the acceptability of the risk. That's exactly what the simulator is doing. What is an acceptable risk level? Well, current risk is driven by the analytical process quality and apparently the quality management process. Glucose. How many methods could achieve a 0.1% risk level? In the group from 2012 to 2014, only 1 of 34 QC samples had a risk above 0.1%, and it was 0.12. In the year 2000, when they did not use QC software, 25% of the samples had risk above 0.1%, and the highest risk level was almost 6%. But back in the year 2000, when they used QC software to every month manage that question of where am I relative to where I want to be, they were as good back then as these labs are now. Isn't that interesting? Can you use an acceptable limit of 0.1% for glucose? Quite possibly. And if we can, why not? But for sodium, don't try that. It simply doesn't exist. If the allowable error limit we're using, the 4.0 based on CLIA, if that is the right limit, then 34, 46, 20, and look at that, only 20% of the methods back in the year 2000, 20% of 51 QC samples then were unable to meet this standard. 35% are now. That's what happens when you manage quality regularly, saying, is this where it should be? I had not looked at that data before. That's why I sound so surprised. What we're using is a process that says where you are, the measured values of the current mean, the current SD based on fact, compared to where you want to be, the measured peer mean, and the medical opinion of the medical goal and acceptable risk level, With those numbers, you can mathematically calculate the percent of results that are currently not where you want to be. You can calculate the number of SD that you can shift from where you are now until you're no longer where you want to be. Or you can do what's currently recommended today, and you can calculate a sigma metric.
I'm almost embarrassed to tell you, but this formula is mathematically incorrect. You are coming to a point where you're going to have to choose how you're going to measure risk. There are at least 4 ways that I know of to calculate sigma. There is only one way to calculate margin for error, and there really is only one truth. If you have a method with a peer mean of 100, a current mean of 110, a current SD of 10, I took my medical goal out to 40, the bias is 10, the total error is 10, and sure enough, the total error as a percent is 30%. But if you calculate bias and standard and CV and add them up, you don't get 30%. And if this method really did have a CV of 10% and a bias of 10%, then it would have a total error of 32%, not 30. If the bias is low, the opposite happens. You're going to estimate the total error at 30% when it's actually 32, or you'll estimate it at 28% when it's actually 30. If we take the numbers to calculate margin for error and sigma, so sigma is simply your margin for error plus 2. The margin for error is how far you can shift until your risk becomes unacceptable. Sigma is the number of standard deviations between the mean and the total allowable error limit. By the time you reach 0 sigma, for the 8% of you who said that was okay, you have 50% failure. Watch it. I'll take that up to 110. The number of patients at risk is 50%. The margin for error is -2, but let's calculate sigma. If you calculate sigma from the percents, in this case you're going to get a sigma value of 0, same as we got. With a sigma value of 0, there's a 50% error rate. Let's bring this back to something a little more reasonable, or maybe, whoops, up in the realm of 105. If the mean is 105, if I choose to calculate margin for error and transfer that to percent and transfer that percent to the number of medically unreliable results in a month, I get 187. If you calculate sigma from percents, if you transfer this to percents and then calculate your sigma, you'll think there's only 130 people at risk. We asked about long-term and short-term sigma. 6 sigma comes with a built-in assumption of a shift of -1.5 sigma to long-term.
We're back to a new recording to see if we can add a little bit of clarity or a little more confusion to the idea of 6 sigma. And I do apologize for speaking badly about 6 sigma. I know it is near and dear to the hearts of many of you, but please hear me out. I think there's things that we're missing, and I'm just not sure that this industrial process belongs in the medical lab. Consider this. When we voted, they went anywhere from 8% said 0 sigma was acceptable, and 28% said no, it's got to be all the way up at 6 sigma. Had I phrased that question differently, I think the answers would have been very different. If you translate the sigma values into the number of medically unreliable results, you find that what we just voted for here was acceptable risk of medically unreliable results somewhere in between 1 in 2 and 1 in a billion. How many bad results are you willing to report? And if you're using the sigma metric, this is in essence what you were saying. A sigma of 0 is a 50% failure rate. A sigma of 6 is 1 in a billion. A sigma of 3, 2, wherever you set that sigma, determines the percent of results that will fail, that you'll allow to fail, and the number of medically unreliable results. So for those of you who said, I would accept a sigma of 0, what you're really saying is I would accept 1 in 2 results being medically unreliable. However, if you said I want a sigma of 6, then you want it to be 1 in a billion. You may not be able to attain that goal. And then we added the complication of, was it a short-term sigma, a long-term sigma, or what is the difference? And this is why I say 6 sigma I don't think works the way it is in medical labs. Here's the real kicker about 6 sigma. Most people don't even know there's a difference between short-term sigma and long-term sigma. And yet, part and parcel of the 6 sigma concept is a difference between short and long-term sigma of 1.5 SDs, 1.5s. So the fundamental assumptions of 6 sigma are unknown or unclear to most people in the lab. We had almost 100 people vote on that. If you calculate risk using the measured values, you get a different number than if you were to calculate sigma from percent, and that's why you need to choose. Look what happens if you calculate the percent risk. Simply take the margin for error. Margin for error you can calculate in your head. It's the error you're allowed minus the error you've got, your total error, divided by the SD. If you add 2 to that, you've got a z-score, which is the same thing as a sigma, or it used to be. You can go to the website and you can say for a given z-value or sigma, you can calculate the percent risk, or it's about 1 in 741. So a 3 sigma method, if that's a short-term sigma, is 1 in about 0.1%. If you wanted to say, I want to set an acceptable risk level of 5%, then you'd say my acceptable sigma is 1.65. If you want to say, I want 0.1% error rate, as you can achieve for those glucose, you'd set your acceptable sigma level at 3.1. There is an assumed shift in sigma, in 6 sigma, that they automatically adjust by 1.5 sigma to recognize the tendency of processes to shift over the long term. The 1.5 sigma shift may or may not be an accurate estimate of the actual long-term instability of your process. This is from morestream.com. Here's another sigma explanation. 6 sigma actually translates to about 2 defects per billion, and 3.4 defects per million that you normally think of as 6 sigma is really a sigma value of 4.5. Where does the 1.5 sigma difference come from? Motorola, back in the 80s. I cannot see any reason to expect that viral load technology, immunochemistry, all of the things we do, the ELISA methods, etc., have the same z-value difference as Motorola in the 1980s. And again, at this site, they say given adequate process data, you can determine the factor most appropriate for your process. I can't resist an opportunity to either share the confusion with you or at least show you that there really is confusion concerning sigma, 6 sigma, z-scores, and sigma metrics. This is a z-score calculator. This is the same as the sigma value, in as much as sigma is the number of standard deviations between the mean and the total allowable error limit. You can come in here, calculate, put in a z-value, and calculate the percent risk. So 1.65, as we've said, equates to a 5% risk level. If your sigma value is 3, that's only a 0.135% level. Here, on a z-value table. However, come to a 6 sigma table and things are completely different. This is a sigma conversion table. The 1.5 SD shift may or may not be an accurate estimate of your process. Come here to a sigma of 3. It tells you that there's a 6.7% risk rate. 66,000 out of a million is 6.7% risk. So here, with a z-value of 3, it's 0.1%, but on the 6 sigma scale, it's 6.7. Thank you, Dr. Westgard, for all the tools you provide us, but it shows the same thing about sigma. If you have 5 defects out of 100 and calculate the sigma value, it tells you your sigma metric is 3.2. But a 5% error rate typically goes with a 1.65% sigma. If you come down here, enter your quality requirement, your allowable error limit is 10. If you have an observed bias of 6, an observed SD of 2, 6 plus 2 times 2 is 10, your total error equals your total allowable error, but your sigma metric is still 2. With a sigma metric of 2, according to this table, that's a 31% error rate. But we're not sure what's a long-term sigma, what's a short-term sigma, and does this shift apply to what we're doing, or is it something that belongs in industry, or is it something that should be that 1.5s shift, should it be qualified to be specific for the method that you're using, or should we just measure sigma on a regular basis?
You can convert margin for error, or sigma, if you calculate it from the same numbers, to a percent. You can see the margin for error of -1, a sigma of 1, equates to 16% failure. I've seen surveys and studies where they reported an average sodium sigma of 0.8. That means on average more than 16% were failing the medical goal. We need to do more than measure sigma. We need to think about what it's telling us in terms of patient risk. And again, it is so easy to teach margin for error. Current risk is driven by analytical process quality and the quality management system. We saw this, that in 2012 to 2014, 5% failed, had more than 1% failure, but almost 15 years ago it was only 3%. So we think we've progressed, but this doesn't seem to reflect it. In that group, acceptable risk, the group from 2012 to 2014, the difference was 95%, 90%, 96%. Not a huge amount of progress in 15 years for current risk. You have to detect all of these problems. You have another black and white choice. Can you do this without stable sample QC? Yes or no? If you have to do stable sample QC to detect an error, then how often do you need to do it? I'm going to review this. We saw it last week or 2 weeks ago. Which of these products can you ship before verifying it meets customer specifications? Was it ever truly, really proven that we should report patient results before checking the QC? Here's what happened when we checked the ability of QC. We simulated a clinically significant error. This group, in 2012 to 2014, only 17% of them could detect that error in the first run versus 39%, 60%. The principle of testing QC samples is that what happens to your patients happens to your QC sample as well. What if the method really failed back here? At the least, the ability of the QC procedures to detect medically allowable error should be evaluated. What is the potential risk if the method fails. We're going to go back into another simulator. We're going to look what happens if you do the mathematically optimized QC process versus what happens with typical lab QC. The lab controls these four numbers: QC chart mean, QC chart SD, QC rule, QC frequency. With those four numbers, by adjusting those four numbers, you can maintain whatever acceptable risk level the medical director has set, or you can shut down the method and improve it. Take it back to him or her and say, what do you want to do now? These three numbers, chart mean, chart SD, and the QC rule, drive the two outcomes. Are you able to detect unacceptable risk immediately, and how many runs would it take to detect that unacceptable change? So we simulate a shift after the blue line, risk is unacceptable. You can see here it's probably going to take 2 runs. One number drives the acceptability of potential risk, and that is the QC frequency. We're going live again. So come over here to QC design. The current risk is reflected in the margin for error. Select a QC process to match the margin for error. So what we're going to do is we're going to look at the margin for error. We're going to come over here and say, for this margin for error, for this range, which means from this percent to this percent, or from 1 in 52 million to 1 in 3 million, and then you get right down here to say 1 in 44. If I get down to 1 in 44, I've decided I'm going to stop. If I'm above that level, then you need a full QC strategy. The frequency of the QC samples, the type, the number, the statistical limits, they don't need to be rules, they're statistical limits, the frequency of looking at your charts for shifts and trends, and the action to take. There's much more to QC than just a QC rule. So you can adjust the QC rule, you can adjust the sample frequency, you can adjust the QC chart review, you can adjust the supervisor's review, you can recommend specific action, and you can see how this could all be easily just driven straight from the numbers. There is the link here. This neat place will let us convert any sigma value, any z value, to a percent or vice versa. So let's come back over here. This is our risk evaluation chart. This is the change chart. This is the tab we're going to use to decide how many runs to reject. So now I'm going to simulate a clinically significant error. I'm going to simulate a shift so that 5% are failing. This has a margin for error of 0.5. That is an extremely small margin for error. You're not going to detect a shift of 0.5 SD. That's a sigma of 2.5, by the way. This is a sigma of 2.5. This QC chart right here, this is a test with a sigma value of 2.5 using a 1-2S rule as a reject, and that's what it looks like. This is a shift of half an SD. Now, if I can bring this mean back to 100, I've changed my mean down to 100, now my margin for error is 3, now my sigma value is 5. Now let me get those drawings off here. Now I don't need the 1-2S rule as a reject. Now I can go in here with a margin for error of 3. I come over here and say I can use a 2.5S rule. So I come over here, I say I'll take a 2.5S rule. Now that I can see that there are 0 false positives beforehand, the odds are still pretty good that I'm going to detect that change in the first run. So I can say yes, probably, not likely, or no. I'm going to say probably, and I'm going to note this as the estimated runs to reject as 1. The trick is, what does the lab do? Most people, and you can look in the mirror if you like, at least double the standard deviation on the QC chart. A lot of people tend to use the same QC rule for all. When you double the number on the QC chart, what happens is you've doubled that, so you've doubled the QC rule. What the lab did with their QC, they doubled the SD on the QC chart, and they're never going to see a QC flag. Never. So will this detect change? No. Runs to reject? Good grief, it could be 20. If I come back here and I'm going to put the assigned SD on the QC chart, I put the 2.0 on. Now this method, so I've got a mean of 100, an SD of 2. This one is using a 1.3s and this one is using a 1.2s. Look at the difference in the error detection after the QC flag, after the reject, after this simulated shift. The QC rule you use and how you assign the values on the QC chart determine exactly the number of runs to reject. The runs to reject times the number of people, or times the number of people in a run, are the number of people at risk. Ray, did we have piled up questions? I'm just bombing on here.
Yeah, nothing yet, Zoe.
Perfect. Okay. I don't know if everybody's shocked or just they're agreeing with me. I hope it's the latter. You can see here there's more to a QC process, and that's spelled out very, very clearly in both IQCP and EP23. There are 5 parts to a QC process. You get them from here. You can look at sigma values. You can look at margin for error. You can't really use the percent risk. They get down to such small values. But it is fascinating to look at what you're really doing here for 1 in how many patients. So you could tell your patients there's a 1 in 44 chance something might happen. Here's what happened. We looked at 605 QC samples. These ones on the right are from 2000 to 2014. This is both the same set, actually. These are both the same QC samples from the same methods. On the right is actually how the labs did quality control. On the left is what happens if you mathematically optimize it. So if you pick and choose the proper rule for each QC chart according to the margin for error, and you put the real values on a QC chart, you can more than double the number of methods that are able to detect a clinically significant failure in the first run. So all the studies that have been done on the numbers of lab errors, whatever the numbers are, you can argue them. But if you're using a method that has hazards that are only detected by statistical QC, then you should be governing your statistical QC to detect clinically unacceptable risk. Here's why this happens. Everybody does QC differently. I've done this survey and it's still up. Some of you have taken it. Everybody takes their mean, their SD, and their rules for the QC charts from a different place. That's not how it's written. That's not the theory, but it certainly is the practice. The optimum QC process is a calculation. It's not an opinion. This is what people do. This is the study that we were looking at. These are the 33 labs. This is the measured CV on the bottom on the y-axis versus the assigned on the top. This is a measured CV of 4 with an assigned CV of 20. Almost unanimously, they have assigned the SD higher than it really is. When you assign the SD higher than it really is, that means the QC rule is going to take longer to detect a clinically significant error. It's not changed in 15 years. This is from the year 2000. This is what they did then, and it's broken down by different analytes. This is around the world, around departments, around every lab that I have ever been into. People have missed the very fundamental instruction to put the mean and SD that you measured on the QC charts. When computers came in the 80s, they created the ability for people to do things wrong so easily, and we just picked it up and went with it. If you use a mathematically optimized process to select QC rules, as the analytical process quality becomes better, you lower the potential risk and you lower the runs to reject. But that's not at all what we see in real practice. This is another example of it. This is with statistical QC on the left. So this is what the labs are doing on the left versus the old software that was around in the year 2000, and you can't even buy it anymore. No runs to reject above 11 versus look what's going over here with statistical QC with the number that will never ever detect a clinically significant failure.
Individualized quality control is far from a new idea. It has been recommended since at least 1989 when Dr. Westcard published QC selection grids. This is a modification in a QC strategy table that I published in the year 2000-2001. Back here, we were selecting the QC rule, single rule, or multi-rule, and adding QC chart frequency, increasing the control frequency, and initiating corrective action, individualizing the quality control based on how good is your method, how far can it move before you're in trouble. We measured critical systematic error every single month for every single QC sample, 5 disciplines across 6 hospitals. This is sodium. Remember, sodium we talked about runs a very low margin for error or critical systematic error. It went as high as 5 down to 0 at the lower level with a mean of 119, and we saw similar shifts at the mean of 142. There were critical systematic errors of basically 0 to almost 5. When that critical systematic error changed, when you came closer to your allowable error limit, we would tighten up the QC rules. Remember the difference that it made in the sodiums? AST, a different but somewhat similar story. High margins for error or critical systematic error in the realm of 25 to 30 standard deviations that you can shift before you're in trouble. However, with this reagent lot, that dropped down to almost 0. So when that reagent lot was in place, we used tighter quality control to make sure it didn't slip over this low end. Then you'd loosen off the QC, and with this reagent lot, it came a little lower again. But there's no magic 1.5 SD in anywhere here. I don't know if other studies have been done. What we did see is that critical systematic error varies over time for all tests in all labs, and that it's different between control levels. Control level 1, control level 2 did not have exactly the same pattern. If you're choosing QC rules based on critical systematic error, and it's different from time to time and test to test and control to control, I can't see how it makes sense to even think you could use the same QC rule for everything. As a matter of fact, I looked here at just the glucose in this study and separated it out with positive bias to the right, positive bias on level 2 at the top. So the upper quadrant, the controls both have a positive bias. In the lower quadrant, the controls both have a negative bias, but in the upper left and lower right, one is positive and one is negative. Seeing the bias patterns like this and the differences in critical systematic error, we found it worked much better to choose an individual QC process for each level of control.
Here's the other thing that surprised me, and it's the last piece of our puzzles we're going to get to before the end of today. QC frequency here decreased. We have the assumption that the methods are so much better, but look at that decrease in QC frequency. Is that justified? Well, let's go find out. Remember, the determination of the acceptability of residual risk of harm to the patient is based on an evaluation of the potential costs, both in terms of the patient's well-being and in terms of financial liability to the treating parties versus known benefits to the patient. So let's come over here. We had established earlier that we test 30,000 patients a month. Say the average cost of a medically unreliable result, I put it in at $50. So you can come in here, you can change the cost per test, you can change the dollars it costs to do the QC sample. What does it cost you to run the QC sample? And the only other number you can change is the QC frequency. When you come over here, you look that the medical director has set an acceptable risk level of 2.3%. We're going to choose to model a 5% failure. With lab QC, there will be 1,000 patients reported at a cost of $50,000, and you're spending $30 to control quality. With the mathematical process, there are 34 patients, less than $2,000, but it costs you $14. The number of times that you run the QC determines the patients per run. So we have 1,000 patients per QC run, and we're taking 20 runs for a reject. In other words, this method is never ever going to detect a clinically significant failure. So there will be 20,000 patients at risk if this method fails. That means 66% or 66.7% of the patients every month would be exposed to unacceptable risk if you test it this way with a method that will never detect it, whereas if you do your QC with a method capable of detecting error and increase the QC frequency, you're maintaining that magical 2.3%. Let me go over that a little more slowly. Let's go back over here and now we're going to go back over here and we're going to pick a more reasonable QC rule. I'm going to put this down to, let's select a 2S rule. Whoops, just for the fun of it. Now, if I want to, now here's how it works, guys. If you really want to, if you care enough about that method, you go down, you crank your 1,2S to a reject. Now, are you able to detect your error immediately? Absolutely yes, and absolutely 1. So this will have even higher error detection than this. Now if I come over here to evaluate the risk, they both have 1 run to reject. The medical director set a value of 2.3%. Your observed value is 0.03% or 0.00%. The acceptable risk level is 2.3%. When you say I will accept the sigma of 2, the margin for error of 0, you're saying I'm willing to accept 683 bad patient results and absorb a cost of $34,000 for these results that can fail every month, and I'm not going to design a QC system that is going to detect them. The standard that's used in this scenario is 2.3%. If that is the standard, you are allowing 683 medically unreliable results at a cost of $34,000. If you do your QC this way, you're going to spend $2,500 as opposed to $1,700. The computer will sort out for you, is the risk acceptable? Is the risk not acceptable? And then you come in and say, is this risk acceptable to me? This is the mathematical calculation. Now you come in and say, okay, with what I know, I'm going to say it is or it is not acceptable. And if it's not acceptable, I have a series of choices. I'm going to assign the recent mean and SD on the chart if it is acceptable. I'm going to implement the optimized QC rule. I could increase the QC frequency. I could decrease the QC frequency. I could improve method accuracy. I could improve method precision. I could change the acceptable risk level, or I could change the medical goal. If you can't meet them, change them. So you can come down here and pick up to 3 things that you're going to do to improve the system. We are at 321. So if you do more QC, you do get less risk. How are you going to get from here to there? Define medical goals, define acceptable risk levels, estimate the current risk, evaluate risk. If current risk is unacceptable, stop, estimate the potential risk, what percent of results will be exposed to unacceptable risk after a simulated clinical failure, evaluate that risk. Is it within defined limits? Then you're good. If you're not, implement the optimized QC process. If it's still not good, improve accuracy or precision, modify your QC frequency, increase the chart review, improve or replace the method. We're really changing the process. We're not changing the numbers. We're not changing the numbers you need. We're looking at it from the perspective of risk. So instead of using TEA limits based on state-of-the-art statistical limits defined by lab scientists, we're going to use medical errors and acceptable risk levels, medical goals and acceptable risk levels defined for general clinical settings by medical practitioners. Then local medical goals and acceptable risk levels can be managed by the medical director in conjunction with local medical practitioners. We can replace those inconsistent methods with automated QC process design that is verified to alert staff immediately to unacceptable risk levels. Instead of inconsistent and unverified response, we could use verified educational and competency assurance to confirm staff action to mitigate risk. Every single college and university teaches quality control differently. There is no individual QC exam for quality control. And if we do this, if the method fails, we can maintain a system. You can set your acceptable risk levels and say, I will never go below this limit. That is possible. How many specific hours of QC education did you or your frontline staff have during your basic training? I saw this on LinkedIn just yesterday, I think. Can you create a Six Sigma Green Belt in a 5-day class? I've asked this at different workshops and people have said, 5 to 10 hours to virtually none. If we can teach this process more simply, we could really, I believe, make a difference. Now the question is, am I right or am I wrong? And the only people who can answer that is you. So if I'm right and you think I'm right, then you need to speak up, because and if I'm wrong, please tell me. I think if we do this, we can save millions of people and billions of dollars. I think this works as a quality process that, in my mind, is better than Six Sigma, but that's in my mind. It's really up to you. I have created this site, thanks to Awesome Numbers that sponsored it, where you can come in, get more information, collaborate if you want to do something. If you want to dig into these numbers, come dig. I'm kind of sort of a one-man band on this right now. If you can support this in any way, please do. The brown bag session is sold out. I just got the roster yesterday. Perhaps some of you are here. We are doing a poster, risk-based grades, an alternative to Sigma metrics, and Randox will be in booth 1335. We will be also making this simulator available once I've repolished it again, and making it available, unfortunately not free, but as economically as we possibly can. This lets you see, I hope you agree, this lets you see how quality control works. It opens it up and removes the misconception, and it gives you a tool that you can use to verify the effectiveness of the QC that you're doing. I'll also send you, there's a little worksheet that you can do just to manually throw some dots on and look at what's happening in your lab. Because if this is happening and you can double the QC effectiveness, we should look into it. That's my lecture for today. I thank you so very, very much for listening, folks. Please send feedback. I would appreciate hearing your comments. If I'm wrong, good heavens, join me. We'll have another webinar. Please prove me wrong, but do it with numbers. And if I'm right, I'll be writing one more message to you to ask for support, at least a petition to sign where we can say this idea is worth looking into.
Thank you, Zoe. On behalf of Randox Laboratories, I would just like to say thank you again to Zoe for the interesting webinar, and thank you to everyone for attending. If you would like any more information, you can visit randoxqc.com, or you can visit us at AACC later this month at booth 1335. Thanks again.
And I will close the webinar.